Hi, and welcome back to Statistics 1. We're up to Lecture 6, and the topic of today's lecture is measurement. As I mentioned in Lecture 5, most intro stats courses and most intro stats textbooks don't spend too much time talking about measurement issues. But for me, this is a really critical issue, and I feel should be a fundamental part of an intro stats course. So we're going to devote an entire lecture to just core measurement issues. So in this lecture, we're going to divide it up into 3 segments. In the first segment, I'll talk about reliability. In the second, I'll talk about validity. And in the third, we'll revisit this idea of random and representative sampling. So in this first segment, let's look at reliability. The important concepts or topics to take away from this are this broad theory that's known as classical test theory. It's also known as true score theory. It comes out of psychology, specifically psychometrics. And I'll explain just briefly what classical test theory is about. And then we'll talk about how to calculate reliability estimates. So how do we know how reliable our measures are? And to be clear, what I mean by a reliability estimate is just if I use an instrument to measure some property one time and then I use it again, the measurements from time 1 to time 2 should be stable. So just think of a scale. As you step on a scale, you weigh yourself, you get off, you step on it again, you should get about the same exact weight, right? If it's a reliable scale. That's all we're talking about here is, do we have reliable measurements? It's a little bit harder to evaluate reliability when you're dealing with things like intelligence or personality or attitudes. Weight and mass, those things are easier to assess reliability. So how do we do it with these fuzzier constructs that are common in the social sciences? Well, that's where classical test theory comes in. So these raw scores I've been talking about, that I've been giving the letter X to, they're never perfect in the social sciences. They're influenced by bias. They might be just influenced by chance error. They're influenced by all sorts of factors. They're never perfect assessments of whatever construct it is we're setting out to measure. Even body temperature, which is a pretty concrete example, is susceptible to bias and chance error. For example, with body temperature, there are different methods to assess body temperature. You can assess body temperature orally, internally. There's this new thing called an infrared thermometer wand that you can do. Each of those gives slightly different measurements. There could also just be random chance error. So if I'm trying to measure body temperature of my partner and he just took a swig of cold water and I didn't know that, then I'm going to get a cold reading, and that's just random chance error. So measurement is always susceptible to chance error. It's always susceptible to, or has the potential to be susceptible to bias. So here's the heart of classical test theory, is in a perfect world, it'd be possible to get the true score for whatever it is we're trying to assess. So it should be possible for me to get the true body temperature. But I can't. There's always going to be just chance error. There might be systematic bias. So any raw score X is actually the true score plus some bias, if it exists, plus some chance error. And as I said, this is also known in psychometrics as true score theory. So as a measure X approaches the true score, it's considered to be reliable. The problem there is we don't know what the true scores are. Right? If we can't actually get the assessments of the true score, then we can't judge how far we are from the true score by looking at the difference between raw scores and true scores. So we just have to estimate reliability. And there are several ways to do that, and I'm going to walk you through 3 of them here in this segment. The 3 that we'll talk about, and there are more ways to do this, but I'm just going to emphasize 3, is 1, test-retest. Another is known as parallel tests. And the third is known as inter-item estimates. I'll walk through each of these. For now, let's go back to this body temperature example. Forgive me if I'm harping on this one, but it works really well for several examples, and it'll work again next week in one of the lectures. Then I'll drop it. So 2 more times I'm going to use body temperature. Again, think of 3 different ways to measure body temperature. Orally, put a thermometer in your mouth. Internally, there are ways you can do that. And then with this new wand, if you're not familiar with that, it looks something like this, and all you have to do is just wave it over the forehead of a patient, and it will give you a reading. My partner is actually a nurse, so I'm very familiar with this, and he tells me that these tend to run a little hot. So they have a systematic bias, is what he's saying. They tend to give readings that are a little higher than, say, an oral thermometer. So that's a systematic bias, because it's not that it runs a little hot for men, not for women, or for people with hair and not for people with hair. So it's a systematic bias. For everybody, it runs a little hot. That's bias instead of chance error. So let's go back and look at histograms. So here's a histogram. This is from way back in the lecture on distributions. This is a histogram of body temperature in degrees Fahrenheit. It's a normal distribution. If you're not used to Fahrenheit, the normal average body temperature in Fahrenheit is 98.6. And you can see that's like right about here. So this is a nice normal distribution. I know probably the majority of the students out there are more comfortable with Celsius, so I just replotted it. In Celsius, same exact data. In Celsius, normal body temperature average is 37, and that's like right here. Okay, so we have nice normal distributions. Let's assume these were measured with the oral thermometer. That tends to give distributions like this. Now let's assume we use this infrared thermometer that we know runs a little hot. Here it is in Fahrenheit. We still have a relatively normal distribution. There's this one guy out here, but it's pretty normal. But if you look at the scale of the x-axis, it's just shifted. And you see that the average is now, it's right about 99.5, maybe a little higher, say 99.6. So it's almost like a degree higher, but it's a degree higher for everyone. That's systematic bias. It's not random chance error, it's systematic bias because it's affecting the entire distribution. And again, if you're more comfortable with Celsius, same exact data, just plotted in Celsius. And now you see the average is where are we with the average? It's like right about here. It's approaching 38 degrees. It's like maybe 37.7. So again, it's running a little hot, but it's running hot for the entire distribution. That's a systematic bias. So how do we detect these kinds of biases, chance errors, and how do we estimate the reliability of a measure? Well, the first way I'm going to describe is the test-retest method. So it's very simple, just like this scale example. Just measure everyone twice. Let's take the oral thermometer, measure everybody in a sample, then wait a few hours, do it again, and their measurements should be correlated. There's people who are have a little bit higher body temperature at time 1 should have the same thing at time 2. There should be a strong correlation. In fact, the correlation between x1 and x2 is the reliability estimate. If there's no correlation between measuring, say, your weight on a scale the first time and weight on a scale the second time, if there's no correlation, then that's a completely unreliable scale, right? That's unreliable. The correlation's 0. What that means for correlational analyses is if something correlates with itself at 0, it can't possibly correlate with anything else, right? So the reliability estimate is actually the ceiling for the magnitude of correlation you could ever find with some other construct or some other measure. So that's why it's so critical to have strong, high reliability estimates, because they limit how high your correlations can go as you do correlational studies. So this test-retest method, we just look at the correlation between x1 and x2. The only problem with the test-retest method is it wouldn't detect the bias, the systematic bias in the instrument, right? So if we use the infrared meter, I did that, say, on everybody in a classroom once, I did it on everybody in the classroom again a couple hours later, and the correlation was really high. If I only looked at the correlation, it wouldn't tell me about the bias. I would have to look at the histogram, I would have to look at the mean of the sample. So another method is the parallel test method. This is, let's take two different instruments and see how those are correlated. So the idea of parallel tests is like doing the oral thermometer and the infrared thermometer, seeing how they're correlated, but also comparing their distributions. So this would give us a reliability estimate. Again, the correlation would be the reliability estimate, but comparing the means and the histograms, that would also reveal a systematic bias. So that's the difference between the test-retest and the parallel tests. Now I'm going to finally drop this body temperature example for the third method and talk about inter-item estimates. And these are actually the most common in the social sciences, because test-retest and parallel tests are actually hard to do. When we conduct research in the social sciences, we're often doing research on human subjects, and that takes a lot of people's time and often money. So it's hard to get them to, say, take one assessment and then come back a couple weeks later and just do it again so that we can get a reliability estimate. Instead, as we try to build in a reliability estimate in one measurement, in one time point. So let's go back to the idea of the personality surveys and assessing extroversion. Suppose we had a 20-item survey that was designed to get at extroversion or agreeableness or any one of the personality traits. What's typical is we'll administer several questions that get at each personality trait. So if you remember back to the personality, the correlational studies lecture where we talked about personality, there was one question that got at extroversion that said, I'm the life of the party, strongly disagree, strongly agree. And then there was another one that said, I don't mind being the center of attention, strongly disagree, strongly agree. There are several like that built into the survey, and what we can do is look for correlations among those items that purportedly measure the same trait. What we can do to estimate reliability is just take half of the items that are designed to get at extroversion and call that subset A, and then take the other half and call that subset B. Now we have two assessments of extroversion built into one assessment, one overall survey. If they're all getting at this one personality trait, extroversion, then subset A should be correlated with subset B, and that correlation will be used as the reliability estimate. This is a very common method in the social sciences. It's called inter-item estimates of reliability. So to summarize this first segment on measurement issues, the main topic here is reliability. And I introduce reliability by just giving a quick overview of this very broad theory in psychometrics called classical test theory or true score theory. And then we talked about three ways to get reliability estimates: test-retests, parallel tests, and inter-item estimates.